And please allow me to introduce our next presenter. And Martin, while I'm doing this, feel free to set up your screen share. Okay. So Dr. Martin Gila received his PhD in analytical chemistry from the Institute of Chemical Technology in Prague. And since 1998, he has worked with Waters Corporation in Milford, Massachusetts, participating in column sample preparation and research, instrument research. So Martin is a scientific fellow in the separations R&D group at Waters Corporation. He has more than 30 years of experience in separation sciences, including chromatography, electrophoresis, and mass spectrometry. His research interest is the analysis of biopolymers, peptides, and nucleic acids. He has published over 75 peer-reviewed papers, and Dr. Gila is a recipient of the Yaroslav Janak 2022 Medal and Chromatographic Society Jubilee Medal in 2023. And with that, please let me hand over to our next presenter. Welcome, Martin.
Thank you, Marcus, for the introduction. I hope you can see my screen and hear me.
Yes, I can.
Very good. So let's go to presentation. I work for Waters Corporation, and I have in maybe last 20-something years analyzed nucleic acids, and all that knowledge was then applied to mRNA analysis. So earlier when we started with antisense oligonucleotides, it was relatively simple to analyze short oligonucleotides like the antisense oligonucleotide shown here. And then when we apply it to much larger RNAs like guide RNA 100 mers, this now challenges what we can do, but we still can manage. However, when we look at the long mRNA, to analyze and resolve long thousands of nucleotide long RNA is a challenge. So in those cases, as it was already mentioned, we use the trick of enzymatic cleavage that converts these large molecules into oligonucleotides that we handle very well in LC and LCMS. And I will show you some examples of that. So Waters has multiple solutions. We are tool makers. We analyze and we make liquid chromatograph instruments and columns as well as sample prep. So today I will talk about several modes that are applicable to nucleic acid analysis: size exclusion, ion pairing, reverse phase chromatography, HELIC. And I will skip some others. I will not mention sample prep, but I will briefly mention enzymes and standards that we provide for nucleic acid analysis. And of course, on one slide, if we can analyze it, we can also use those columns for preparative purposes. Ion pair reverse phase chromatography is now classic method for analysis of nucleic acid oligonucleotides. And that is because it could be used directly with LC and LCMS. And here I show an example where we try to push the separation for oligonucleotides up to 100 mers. This could be done with an efficient columns, shallow gradients, efficient ion pairing systems, in this case hexyl ammonium acetate. And as you can see, we can resolve an N-1, let's say up to 60, 70 mers. The longer oligonucleotides are less well resolved, but the resolution is still usable. So if you could apply this for analysis, you can resolve even the N and N-1, which will become apparent why this is useful in later slides. So we can resolve these long mers. The thought behind that was, now we have these sgRNAs that are 100 mer long, and can we analyze them and can we purify them? So in this case, I show a bigger column, 4.6 by 100 millimeter long, and with 300 angstrom pores. The wider pores are more suitable for these longer nucleic acids. And you can see, if you would count all these impurities and peaks in a crude synthesis of sgRNA, 100 mer, you would see there is about 95, 97 peaks that you can count. The N-1 and 2 are eluting on the front of the main peak, and you can assess visually how pure that 100 mer oligonucleotide is. If we can separate it, we can also purify it. Here I show that you have already seen that black chromatogram on the previous slide. Now I start to load much more on the column. This is not a prep column. This is still 4.6 millimeter ID. Yet we can do a lab scale purification, let's say up to tens of 100 nanomole. When you load more, obviously you will get slightly wider peaks, slightly overloaded columns, peaks also shift, but you still do have the separation. If you want to isolate the 100 mer, I would recommend starting fraction collection somewhere close to the peak top. Don't be greedy, because on the front, as I said, are your N-1 and 2 impurities. And I would also stop collection somewhere in the mid of the peak height, because on the tail, those are the N+ impurities and so on. If you wish to push this further into a more preparative scale, there are obviously preparative columns that are up to 50 millimeter ID. And for those, you can purify gram amount of material in a single injection. Let's move to a next mode. So beyond ion pair reverse phase chromatography, we have another mode. It became popular after 2015 with the first publication, and that is HILIC. For non-chromatographers, I will say this is hydrophilic interaction chromatography. It also uses volatile mobile phases, so it could be directly connected to mass spectrometry. And on the right side, you see that we have a good resolution, not as good as ion pair reverse phase chromatography. But one reason why we like the HILIC columns is that they offer alternative selectivity to ion pair reverse phase chromatography. For example, on the next slide, I show you this sample. You can see the sequence. It's a heavily modified oligonucleotide that is also linked to C16 alkyl chain, palmitoyl. Now these oligonucleotides are being used for drug purposes because the alkyl chains acts as a delivery mechanism. In this case, this particular sequence is one of the standards that Waters provides to our customers if you want to develop methods for these type of oligonucleotides. You can see that HILIC handles this separation rather well. I must say this particular oligonucleotide is a challenge for ion pair reverse phase chromatography because it is so hydrophobic, and that alkyl chain competes with the ion pairing, and the reverse phase chromatography. So HILIC, in this case, is the recommended method. You could also see that our peak 1 and peak 2 have the same mass by mass spectrometry. This is because those are two diastereomers that are created by phosphorothioation of the backbone linkage. So we can resolve that, we can resolve N-axis, etc. As I said, HILIC is a good as an alternative selectivity chromatography. In this slide, I'm showing you size exclusion chromatography. So size exclusion is a low resolution technique. It has been used for many, many years, but rarely to nucleic acid separations until recently when we started to work on it. And you can see that in this case, I wanted to tune my separation to oligonucleotides in the length of, let's say, 30 to 150 mer, in keeping in mind that this is the length of poly-A tail of mRNA that I want to interrogate. So I was looking for a suitable size exclusion column with a pore size and started with 125 angstrom. This gives us resolution, better resolution for short oligonucleotides, actually quite amazing resolution, even N-1. But for this particular range, up to 150, 250 angstrom pore size was the right one. I also tried the bigger pore size, 450, and that one is beyond the optimum, but it starts to resolve intact mRNA based on the size. And obviously, if you want to do intact mRNA analysis, you should go for the wider pores, like we also offer this 1000 angstrom pores, etc. So speaking about 1000 angstrom pores, size exclusion, this is a new column in the GTX Resolve family. It is premier surface, so non-specific adsorption is suppressed by this, and it has a 1000 angstrom pores size, and we developed the column in mind to be used with MALS, multi-angle light scattering detector. To explain, in MALS, the bleed from the column and any particles that come out of the column are very detrimental for the MALS analysis. It creates noise. So this column has a very low noise compared to other competitive columns that are out on the market, and it also has a high resolution. Talking about MALS, let me show you the application. So this is the same column analyzing an intact mRNA, and we have a PEEK2 that is the main compound, and as well as some other. So I should notice that mRNA is very difficult to be analyzed by mass spectrometry, because now we are talking about megadalton size molecules, and there is also a trick. The tricky part is the poly A tail has an inherent microheterogeneity. So instead of looking at one mass, you're looking at wide range of masses, and that is true challenge. So for MALS, we can look at the main peak and get the molecular weight. That's the y-axis here. And it comes exactly within a few percent to the expected molecular weight. In case you want to look at some other peaks, like what is this? This is about double of that molecular weight. So it's aggregate, it's dimer. And you can see the higher order aggregates there as well with much higher molecular weight. And now we get to mRNA. As I several times mentioned, this is challenge to analyze. So we can use the trick of using selective enzymes to chop the portions that we want to investigate, either 5' or 3' end, with, in this case, 2 different enzymes. And later on, I will show you the analysis of the entire mRNA after the digestion. So first, let's have a look at the poly A tail. This is the very reason why I looked into size exclusion column. This is the 250 version angstrom pore size that resolves well these 150 down to, let's say, 50 mer poly A tail. And the analysis goes as follows. I have a fluciferase mRNA of this size, the intact molecule. This is where it elutes in size exclusion. If I expose it to RNase T1, within 15 minutes, I can accomplish the full digest. My green peak disappears, and I have plenty of short oligonucleotides down to mononucleotides. And then this peak, which is the longest of all, and that's the poly A tail. I liberated my poly A tail from the mRNA, and because the size exclusion is sizing the molecules, I can assign based on my calibration that this peak is 127 nucleotides long, and that's my poly A tail. For comparison, here I include 100 mer synthetic standard of oligoRNA, and you can see that it elutes past, so it is shorter. All of these are synthetic impurities that you will see on the next slide. So this method is very simple, 15-minute digestion, 15-minute run, and you get your answer. However, this is a low resolution technique, as I mentioned, and we do not get much information about microheterogeneity of this poly A tail. If you want to resolve this peak into N-1 versions, or all versions, microheterogeneity of poly A tail, you could go to IMPR reverse phase chromatography, In this case, this is 300 angstrom version column, a long one, and shallow gradient. And here I use the same sample, actually different mRNA, but the same method. I digested this intact mRNA into all sorts of oligonucleotides with RNase T1, and I liberated the poly A tail. And this is the separation I get. I could get N- separation up to, let's say, 150 mer, not complete separation, but good enough to really assign what this tallest peak is. And I can see what all of these impurities are. You can see that when I spike in my 100 mer oligonucleotide size marker, I can resolve all these N-X and 101 peaks. If I now spike in the same sample another standard 120 mer, this is where it elutes. And if you can count 121, 2, 3, you can assign the main peak. So this is a really high resolution technique that is useful to study the microheterogeneity without mass spectrometry, fully relying on the separation power of chromatography. We could also analyze, as I showed you, the 5' cap portion, and we use enzymes, in this case MC1 enzyme, that cleaves the 5' end and liberates an oligonucleotide that either has a cap portion or the no cap, there is the mass missing. We can detect it by mass spectrometry and extract those particular masses from for cap version. This is the peak where capped oligonucleotide elutes. And if there is no cap, we are extracting this mass, we get much smaller peak, and we can then quantify, at least relatively quantify, what is the content or extent of capped mRNA versus the uncapped. So finally, let's look at what we can do about the entire mRNA and look at the full sequence. The method is called mRNA mapping. And as I said, we use selective cuts with the endonuclease to generate, ideally, it would be 10 to 20 mer oligonucleotides, but enzymes cut with it once, so we also observe much short oligonucleotides. By injecting that particular sample onto an LC-MS, we can do the mRNA mapping and get the primary sequence. And I must say at this point, this is not a de novo sequencing. We do have to know for this method what is the sequence of mRNA. It's just a confirmatory sequencing. Here is one example that, again, it's F-luciferase beta mRNA. We perform T1 RNase digest. And that is the enzyme, if you are not familiar with the selectivity of this enzyme cuts past on a 3' end of a G nucleotide. So whenever there is a G in a sequence, there is a cut, and it produces the beautiful chromatogram of, let's say, from 2 mer to 30 mer, plus that longest peak, if you remember again, it is a poly A tail. I can apply LC-MS, deconvolute the mass spec data, and I get this. And again, it gives me the information about microheterogeneity of poly A tail. We can analyze this 127 plus minus long oligonucleotides. Mass spectrometry is good for that. So now let's have a look at the main sequence and all these oligonucleotides. If we look at unique peaks of these, let's say, 10 to 30 mer oligonucleotides, they have unique mass, and that corresponds to the sequence. So if you look at those, we get 38% sequence coverage. Unfortunately, the remaining peaks, especially the short ones, they don't have unique mass. They have non-unique mass. That's because the RNA building blocks, we are building this polymer, biopolymer from only 4 building blocks, and there is a good probability that some of the short mers will have the same nucleotide composition, hence the same mass. We could still do the analysis of that relying on MS-MS method and really sequence that portion of nucleic acid. And when we include that, we get another 56% of sequence coverage. But ultimately, for the very short oligonucleotides, like 4-mer, 3-mer, those are not very informative pieces that are produced by this enzyme digest. That is why the researchers at Waters have looked at some other good selectivity enzymes for mRNA cleavage, and one of those is MC1. The other one is cosatibin. They have both different selectivity, and they also have different cleavage motifs, dinucleotide motifs, not just a single nucleotide cleavage. I better explain this in this example, and then on next slide. Here we look at the 100-mer sgRNA, relatively simple sample, and we apply 4 enzymes. One of them is cosatibin, MC1, those are the new ones, and then the more traditional RNase T1, also we compare to RNase 4. RNase T1, which is an enzyme that I like, generates relatively simple and nice and clean RNA map, but unfortunately it does produce many of the short mers that are not informative and not unique. So based on simple MS masses that we can detect, we get only 72% coverage of unique masses. Compared to it, all the other 3 enzymes give us 100% coverage. The explanation is that these enzymes cut on multiple sizes and also have produced some of the missed cleavage peptides, meaning, I say peptides, but those are oligonucleotides, meaning that there is a partial overlap in between oligonucleotides that we get, and from that, those overlaps and those additional peaks, we can reconstruct the full sequence. Speaking about the selectivity, so there's 2 new enzymes that are part of Rapizyme family. The MC1 has these cleavage motifs, AU, UU, and CU. Cosatibin has additional motifs, CA, CU, CG, UU. You can see that 2 of those, CU and CU here, are common for both enzymes. Maybe looking at this explains it better. So Rapizyme MC1 preferentially cleaves at those 2, and UU also produces very frequent cleavage, but in addition to it, has 2 additional cleavage motifs. Those are the CA and CG that happen at much lower frequency. So those are the main sources of missed cleavages. Cosatibin has 4 dominant ones and about 3 less dominant ones where the cleavage happens in less frequent fashion. Even though this produces less, I would say, more complex chromatogram and more peaks, this is actually beneficial for the analysis. Showing here, when we apply those enzymes, and I show here the MC1, when we apply it to mRNAs, this is about 1,000 nucleotides long, it produces quite a complex chromatogram with many peaks. Most importantly, many of those are in the optimal range of, let's say, 10 to 30, 20 mer of oligonucleotides that are easy to analyze by LC-MS and have unique masses. So if you look at this chromatogram, you get all the masses that you detected, store them into this map of coverage map, and all of those that are detected and unique are in green color. All of those that are ambiguous, like a UGUC, it occurs twice in this sequence. So It is a mass, it is a unique mass, but could happen for 2 oligonucleotides. So those cases are in pink color. So if we took those that are very unique, from the get-go, we have over 70% coverage. If we take plus the pink ones, we get over 90% coverage for this mRNA without a need to go into an MS-MS interrogation, which is much more complex. So in case that you really need to get a full coverage, then you would apply, besides of MC1, you would apply the other enzymes, and then you would reconstruct a full sequence. So in conclusion, I showed you that we have very powerful ion pair reverse phase chromatography methods that provide an excellent resolution up to 100 mer oligonucleotides. And because this ion pair reverse phase chromatography relies and uses volatile mobile phases, you can easily use them for lab scale purification. Size exclusion, as I mentioned, is a low resolution technique, but now it really gains more popularity for sizing mRNA. I didn't really show you an example, but we can size intact mRNA. And I showed you the application for poly-A tail measurement, 30 minutes, and you get the information about the average length of your poly-A tail. HELIC, it is a very useful method. We have published a couple of papers discussing alternative selectivity of HELIC compared to more traditional ion pair reverse phase chromatography. And I really believe, and I didn't even mention it, HELIC, because it uses such a high concentration of organic in a mobile phase, could be used for deformulation and direct analysis of lipids as well as nucleic acid. And it has been recently shown by my colleagues from Waters how to do it. Ultimately, we can also apply the LC and LC-MS in this case for mRNA mapping using these endonucleases that produce specific cleavages, and this is the new family enzymes, rapizymes, MC1 and cusativins. As you've seen, those maps, RNA maps, are quite complex, and you do need to use and want to use benefit of the software that exists for it. And if you need such a software, we also produce some. So this is the end of my presentation, and I will be happy at the end to answer your questions.